to have Zheyan Wan, who is an assistant professor in BIMSA today, and she's going to talk about CRT fractionalization. Go ahead, Zheyan.
Thank you for the introduction. First of all, I would like to thank the organizers for providing me such an opportunity to report my work. I will talk about CRT fractionalization. This talk is based on my recent unpublished joint work with Zheyan Wan, Professor Yau, and Yizhuang. Before I introduce the notions involved in this title, let's review.
Right enough. Right enough.
Let's review a Nobel Prize work. In 1956, the theoretical physicists Zheng Daoli and Zheng Yang proposed the possibility of parity non-conservation in the weak interaction. And in 1957, Jianxiong Wu's experiments confirmed that the parity non-conservation in the weak interaction. And for their discovery of parity non-conservation, Zheng Daoli and Zheng Yang won the Nobel Prize in Physics in 1957. Now let me introduce the charge condition C, mirror reflection R, and time reversal T. The charge condition C is not a space-time symmetry, so it cannot manifest itself as passive transformations that acts on coordinates, but it can manifest itself as active transformation that acts on a particle or a field. And for mirror reflection R and time reversal T, there are two versions, passive and active. First, for the time reversal T, the passive version looks like this. The direction of time axis is flipped, and while the object does not change. The object does not change, and the other active version of time reversal T does not change the time direction of time, while the objects are flipped. The object is flipped by the time reversal T. Actually, these two pictures are actually the same, but the same thing, but from different perspectives. And the passive version of the mirror reflection R also flips the space coordinates, and it does not flip the position of the object. And in the active version of the mirror reflection, the space coordinate does not change, and the object flips to the other side of the mirror. Why do we consider the mirror reflection R instead of the parity P in this work? Because P is a composition of several reflections, so the reflection R is more basic. And in all the dimensional space-time, the parity P is contained in the special orthogonal group, hence also in the proper orthogonal Lorentz group. So P is not an independent discrete symmetry. For example, the CPT theory should be called CRT theory in any general space-time dimension. And there is a canonical CRT. Well, we observe that CPT cannot be canonical for D equals 0 or more 4. And I will explain the CRT theorem and the canonical CRT shortly. And now we have some questions. First, given the proper orthochronous Lorentz group, how to define the combined CRT symmetry? Is that canonical or not? Or is this unique? And from this combined CRT, how to specify each CR and T? What is the group structure? And what is the fractionalization? And third question is how to relate different dimensions by domain wall picture. How CRT fractionalization changes on the domain wall in D dimension and D+1 dimension. The first question was already answered in other related words, and I will answer the second and third question in this talk. There are some related words. In 2016, Reed and Hopkins studied the CRT theory. And in 2019, two groups of people, Kaysen, Komodowski, and Thorngren, Cordova, Omari, Shaw, and Yan, independently studied the canonical CRT and domain wall dimensional reduction. And in 2021, Zheyan Wan studied CPT fractionalization in 3+1D and 1+1D. And now I'm going to introduce the CRT theorem and the canonical CRT. The CRT theorem asserts that the symmetry H of any relativistic QFT naturally extends to a double cover G of H, and elements of G minus H acts antilinearly, and CRT is an element of G minus H. And so there is, when relativistic QFT, there is a natural CRT symmetry, but it is not unique. Canonical CRT is obtained by breaking all the internal global symmetries. It is unbreakable and unique up to rotations. And the domain wall dimensional reduction requires that the combined symmetry CRT is canonical. So we will only consider the case when CRT is canonical. Now I'm going to introduce the symmetry fractionalization. Symmetry fractionalization means that the matter field is not in the linear representation of the original symmetry group G, but in the projective representation of the original symmetry group G and in the linear representation of the extended group G tilde. A well-known example is the gapped 1+1D SSB1 Horden chain with G equals SO3 symmetry, whose 0+1D boundary can have a two-fold degenerate SSB 1/2 doublet with G tilde equals SU2 symmetry. So we will construct
can you go back to the previous slide? Can you explain what's going on here on this slide? For a person who doesn't know what a matter field is, what is that? What is isospin? What is Haldane chain? What are these things? Can you explain a little bit? Because I'm just completely lost. What's going on? So you have a QFT. Can you give a simplified presentation of what's going on in here? You have a QFT with certain internal symmetry. So what does a matter field mean, for instance? What is it? Is it a section of a bundle? What is it?
Yes, for example, we are going to consider the direct fermions and the Mara fermions, Boyer fermions, and Mara fermions. They are defined as the sections of certain bundles, fiber bundles. And for example, direct fermions can be defined as the sections of a irreducible 24 module bundle or
I can't hear. I can't hear the speaker. Go ahead.
So
please continue.
And we will consider the analogous CRJT fractionalization. The RJ is the mirror fraction with respect to the space coordinate xj, and the CRJ and T are Z2 involutions and commutative with each other for a scalar boson. So they generate the group Z2C times Z2RJ times Z2T. In contrast to a scalar bosons, Z2C times Z2RJ times Z2T, we discover an order 16 non-affine group G psi tilde for dual fermion in all space-time dimensions. And the CRJT fractionalization for dual fermion in any space-time dimension D is a group extension. And so they are the group generated by CRJT which satisfy this that sequence. And our
so wait, going back. So fractionalization, what is it? The definition of it? Is it that decomposition?
It is the total group G psi tilde in this Schroeder sequence.
So that decomposition is the fractionalization. Extension is the fractional. Okay, fantastic.
Our contribution in this work is as following. We determined the CRT fractionalization with the canonical CRT for dual fermions in any space-time dimension, and we defined an H periodicity. We determined the RT fractionalization for Majorana fermions in any space-time dimension D equals 0, 1, 2, 3, 4, more 8. And we determined the C or T fractionalization for wire fermions in any space-time dimension, in any even space-time dimension. And we studied the domain wall dimensional reduction of the CRT fractionalization and RT fractionalization. This is our main result. We prove that for dual fermion and HD, there are two possibilities of the CRJT fractionalization with the canonical CRT. And for dual fermion, the two possibilities of the CRJT fractionalization with the canonical CRT depend only on the remainder of the spacetime dimension D modulo 8. And now I'm going to show you two tables. These tables are complicated, but you can find some laws by your eyes. Dimension. Oh. For example, the two lines D equals 3 more 4 and D equals 4 more 4 are exactly the same, and D equals 0 more 8, D equals 0 more 8 and D equals 7 more 8 are exactly the same. And if we look at the second table.
So to check that these fractionalizations are valid, what would you check?
Because if we quotient by the prime parity, then -1 to the f, we have replaced the -1 to the f by 1. So C squared, RJ squared equal T squared, CRJ squared, RJT squared, CT squared are all 1. So they generate the Z2C times Z2RJ times Z2T as in the scalar boson case. So the quotient group by of this CRJT fractionalization by Z2F is Z2C times Z2RJ times Z2T. And this is the second table. The only difference between these two tables are RJ squared and CT squared. And we will find that the line D equals 1 more 8 for D larger than 1 is exactly the same as the D equals 2 more 8 in the second table. And similarly, we will find other relations. We denote GDI D more 8 by the ith possibility of the CRJT fractionalization with the canonical CRT for a dual fermion. And we find these relations. And we will use these relations later in the domain wall dimensional reduction. And Majorana fermions are defined as dual fermions with the trivial C symmetry. Majorana fermions exist only for d equals 0, 1, 2, 3, 4, more 8. And we also determined the RGT fractionalization for Majorana fermions. And for d equals 2 more 8, there are two choices because Majorana fermions can be massive or massless in d dimension for d equals 2 more 8. And the first choice is for the massive case, and the second choice is for the massless case. And we also find some laws in this table. For example, the d equals 3 more 8 and d equals 4 more 8 are exactly the same. And d equals 2, the first possibility of d equals 2 more 8 and the d equals 1 more 8 for d larger than 1 are exactly the same.
Can you quickly say what is Majorana fermions?
Oh, okay. Dual fermions are defined as the sections of the complex of the irreducible transport module bundle, or the sections of the complex beam bundle. These two definitions are equivalent. And Majorana fermions are defined as dual fermions with the dual symmetry. And wire fermions are defined as the complex sections of the complex semi-spin bundle. And Majorana wire fermions are defined as the fermions which are both Majorana and wire.
By massless, you mean charge.
Hmm?
By massless, you mean charge. Just one component, because otherwise I expect it discontinuous in the mass. So going to 0, of course, if I have only one component, it's different. But if I have both left and right, I expect that it's continuous in the mass. Here, the difference between massless and mass should be between chiral and neutral.
Hmm. I will send this question later. Say thank you for your question. We find we summarize the laws that we find in this slide. And while wire fermions exist only for even d, for d equals 2 more 4, wire fermions have only C symmetry, and for d equals 0 more 4, wire fermions have only T symmetry. We also determine the CLT fractionalization for wire fermions. And we use GW d more 8 to denote the CLT fractionalization for wire fermions. And Majorana wire fermions are defined as fermions which are both Majorana and wire. And Majorana wire fermions exist only for d equals 2 more 8, and they have only the trio C symmetry. And so we use GMW2 more 8 equals C2F to denote the trio C fractionalization for Majorana wire fermions. Now we study the domain wall dimensional reduction. This is the mass profile of a fermion in D plus 1D, and the domain wall is the Sj equals 0. That connects the M positive and M negative, the two domains M positive and M negative. And here I draw this domain wall as the smooth domain wall, but it can be either smooth or sharp. And we have two questions: how CRT fractionalization changes on the domain wall in D dimension, RT plus 1 dimension? This is the third question that I mentioned before. And the second question is, if a D plus 1D fermion is in the board with the mass profile shown in the above figure, then what is the fermion on DD domain wall? This is the case that U is spontaneously broken, so it reached the two degenerate ground states. And so, for example, if U is broken by the mass term, then you can think of the first curve as the mass profile in this figure, and then you switch the two joint bond states, and so we need to combine it with the space orientation reversing symmetry CRJT to obtain the symmetry on the domain wall. So if D is odd, then we have spontaneously broken symmetry U. For example, the mass term breaks the symmetry C and R for D equals 1 mod 4, and the mass term breaks the symmetry T and R for D equals 3 mod 4. And if U equals C is unitary, then it becomes anti-unitary T prime, because U times C RJT equals RJT up to Fermi parity on the domain wall. And if U equals T is anti-unitary, then it becomes unitary C prime equals U times CRJT equals CRJ up to -1 to the F on the domain wall. And if U equals R is unitary, then it becomes anti-unitary U times CRJT equals CT up to the Fermi parity on the domain wall, which is broken because either C or T is broken and the other one that is not broken. And so for all the D, the D dimensional to D minus 1 dimensional domain wall reduction maps Rj to 1 and Ri to 1, because all the R is broken, and C maps to T prime equals RJT, or T maps to C prime equals CRJ. And our conclusion is that for all D dimensional CRJT fractionalization for direct fermion, GDI D mod 8 becomes the CRT fractionalization. The CRT fractionalization for wire fermion, GW D minus 1 mod 8. And GM stream mod 8 is the RT fractionalization for Maillard wire fermion, and it reduces to GMW at 2 mod 8. This is the triple C fractionalization for Maillard wire fermion. Because C becomes C. Here for there is no reduction from GM1 mod 8 to something else, because for D equals 1 mod 8, the C is broken, so C becomes T prime equals RJT. Wow. Well, because for D equals 1 mod 8, the Maillard fermion has to be massless. So for D equals 1 mod 8, or for D equals 1 mod 8, the C should be becomes RJT, but C this case does not exist because the Maillard fermions in D, if D equals 1 mod 8 dimensions, should be massless. So but here the bulk should be D dimension should be massive. So only GM3 mod 8 to GMW2 mod 8. And if D is even, then we do not have spontaneously broken symmetries. So the RJ still becomes 1 because the direction xj is reduced in the D minus 1 dimension domain wall, and I becomes I, and C becomes C, T becomes T. they do not change. And so this is our conclusion for even d dimension to all the d minus 1 dimension reduction is like this. These are exactly the inequalities that we found before. For example, GD1 0 more eta and GD1 0 more eta are exactly the same, and GM1 2 more are exactly the same as GM1 more 8. Here, GM1 more 2 more is the first choice of the first choice of the RT fractionalization for Majorana formula in D equals 2 more 8 dimension. Here we choose the first choice because also the Majorana formula should be massive. So we choose the first choice. It is massive. And we can obtain this result prior to the domain wall dimensional reduction of CRT fractionalization, and this is a consistency check for our result. For example, the arrow, the target of the arrow is the fermion that on the domain wall of the board, which is the source of the arrow, and the numbers indicates the dimension of the fermions, the dimension of the representation of the fermions, and the upper index indicates that it is real or complex. The lower index indicates that it is the chirality, left and right, and so from this table can be obtained by observing that the domain wall, the degree of freedom on the domain wall is half of the degrees of freedom in the box. So we only have these choices, and in this table, the dual fermion becomes dual fermion from even dimension to odd dimension, and dual fermion becomes wire fermion from odd dimension to even dimension, and the Majorana fermion becomes Majorana fermion from even dimension to odd dimension, and the Majorana fermion from D equals 3 more 8 becomes the Majorana wire fermion from Majorana wire fermion in D equals 2 more 8. No, let me finish this talk by mentioning some future directions. First, we can compute the cobordism groups with the symmetry that contains the CRJT fractionalization, and study the mass depth. And we can generalize our result for the flat spacetime to the curved spacetime, and we can study the index theorem. And we can study the CRT Breitheit's Hall, and we can study the stream version of the CRT fractionalization. And we can relate it to the RTR2 framing, which is the fractionalization of the double of tangent bundle, and we can relate it to the supersymmetry. And that's the end of my talk. Thank you.
Questions?
You are getting Minkowski space.
Yeah.
But in principle, we expect that field theory can be constructed in the Euclidean signature and then recrotated to Minkowski.
Yes.
And of course, the Euclidean Lorentz group, which is just SO4, is compact and has very good properties and has less components. I mean, the connected components are if you go to the cover just one. So what your results will be, or there will be less cases if you start with a Euclidean theory and see what may happen in the Euclidean regime, and then recrotate to understand what happens in the Minkowski signature. Because it may be that the Euclidean signature, I mean the Wick rotation, selects some situation with respect to others. Have you tried that?
Actually, for example, do you mean, for example, for example, the CT square equals 1 or equals -1 in this table. In this table, CT square equals 1 or -1 for that. And the CT for the PR formula corresponds to the T on 2 Majorana formulas. And then if for example, if CT square equals 1, then we get T square equals 1 for the 2 Majorana formulas. And so this is the P minus case. If we recrotate to the Euclidean signature. And if CT square equals -1 to the F, then this is T square equals -1 to the F for the 2 Majorana formulas. Then this is the PIM pass case. So to mean you recrotate the special the proper orthogonal Lorentz group to the Euclidean signature and combine with the CRT fractionalization.
More questions? So this seminar really is to kind of educate us, learn about each other's research. So I have no idea about quantum field theory and things like that. So I'm trying to understand this in the most basic level. So you have a space-time, to my understanding, 4-dimensional space. You have the Poincaré group, right? 10-dimensional group. You're looking at some discrete subgroups of this Poincaré group, right? You call them C and T and P. Hossein explained to me, C is the charge conjugation, T is the time reversal symmetry, and P is the parity. Okay, so far I understand. Now you want to extend this group, right? You want to extend it by Z2. Am I right? Okay, you get a bigger group. Now, this bigger group sometimes has fractionalization property, sometimes doesn't. You want to check it does. What is the criteria you check?
Oh, so this is our assumption that this is our assumption that this for the RGR formula and the CRJT, the group generated by CRJT and T is this is in this short sequence. This is our assumption. So and this is the definition of CRJT fractionalization. In general, we did not prove that the group generated by CRJ and T for GR formula is in this group extension.
But I can always take this kind of thing and make many groups. So I can always extend the group and make it bigger.
Yes.
And my bigger group, if your extension is a split extension, definitely that thing that sits in the middle, G tilde, will have CPT.
An extension of abelian group, which is not abelian.
Correct.
Actually,
okay, that answers one. Answers that question. Where does it say?
There are, let me see. the group extension is classified by the second converged class in H2B, Z2C times Z2R, J times Z2T, with the coefficient in Z2F, and the group is Z2 6. So there are 64. There are 64 is such group extensions, but we only obtain we only obtain the 8 possibilities.
Okay, so you extend it, you make it a bigger group, and then you check in all dimensions if your underlying physical theory has that extended group of symmetry.
Yes.
Okay, that's fine. Okay. All right, thank you.
Maybe you can also explain what is the wall.
In details.
It's giving a definition of a wall.
The wall that separates the two domains, M positive and M negative. The wall that separates the two domains corresponding to the M positive and M negative.
We have some representation of one side of the wall.
You have the mass of the kernel is positive on one side, negative on the other. And then on the wall it is smoothly incorporated between plus n and minus n. Is that correct?
So we're trying to understand what happens.
So when you pass from that one, you need to go to 0. And in that point, the kernel is mass. That is the well, the mass. You know, that is mass. So you have propagation of masses and in one lesson.
For us, it's not elementary, but okay. Thanks for the explanation. Ask these kind of questions. If you have now a lot of question marks in your head, this is the expert asking. Sergio, Zheyan, they can answer any questions. Basic questions. There you go.
I have a question. How does the I actually don't understand CRT. How does this CRT relate to the computation of cobordism groups?
I see. For example, that just t squared equals 1, and we only consider t. Then this corresponds to the PIM, the extension of Z2T with by the SO group, SO special orthogonal group. Z2T the special orthogonal group and the parity Z2F is the P minus. Oh, sorry. Maybe I should. For example, if we only consider Z2T, and then this extension can be Z4TF or Z2T times Z2F. And in this case, if we consider the Lorentz group, or we only consider the special orthogonal group, which is the maximal compact subgroup of this Lorentz group. Then we consider the extension of these two groups by this group. Then we obtain the P plus and P minus. So we can compute the cobordism groups.
What is P and P minus? P plus and P.
These are two extensions of OD.
No. So,
it is the extension of the orthogonal group by by the variant parity Z2F. So this we can only consider Z2T, this is it. And if we want to consider Z2C, then we can also have Z2CF, this is equal CF and Z2C times Z2F, and then we will obtain spin times C4 not Z2 and spin times Z2. We consider this and no. So in this case, we should replace it with SOD times Z2. And so there are many symmetry groups that we can obtain if we consider the extension of the CRT fractionalization with the extension of CRT fractionalization by the special orthogonal group or the orthochronous proper orthochronous Lorentz group. So we can compute the cobordism groups.
Right. Okay, please. More questions? Okay, if not, let's thank Zheyan.